Welcome to our third lesson about ROS2. So in this lesson, we are going to automate our last robot that we built in our last lesson. If you remember, we built a robot with 3 different degrees of freedom. We have a body rotation, an arm rotation, and we can even slide the manipulator. In this lesson, we want to generate a pattern of movement, which automatically drives our robot. Let's start by editing our setup.py file. We open the file using our preferred editor, and first of all we need to define an entry point. The entry point is always the name of our program, which can be called by ROS. The second step will be to edit our new robot.py file. In this file we define our main program. Let's start by importing some ROS libraries like our CLPY and the sensor message. The sensor message will be used to control the joint positions. Finally, we import the NumPy library. Let's define the main routine, which calls the main function where we have to initialize our class. This is exactly the same procedure as in the first lesson where we implemented a subscriber and a publisher node. Now we need to initialize our class robot definition by passing the name Udo, and then we let ROS to spin this class over and over again. Let's now implement the class robot definition. The class node must be inherited, since we need many methods from that class. After passing the name of our node to the constructor and its initialization, we can define our publisher as a class attribute. Since we want to send to our robot the joint positions, we need to specify the message, joint state, and the topic, joint_states. We then create an empty message, which header, frame_ID is set to robot. Next, we need to specify the name of the joints exactly as they has been defined in the URDF file. So we have in the following order: body rotation, arm rotation, and the last joint manipulator. You should always check those names against your joint definition in your URDF file. Otherwise, they cannot get recognized when running your program. Since the robot is affixed with the world, we do not need to pass this joint over the joint states topic. This is not only unnecessary, since the joint is fixed, but it leads to problems. In the joint state message, we pass only the joint positions of the joints, which are changeable. Let's go over and define some initialization values for the joint positions in start configuration. Body rotation starts at 0.0, arm rotation at 0.0 and the manipulator at the lower bound, which was defined in the URDF file, in this case 0.25. Imagine the joint state message as a container containing all those values. Our idea is now to update those values in the container on a constant time basis and send them to the robot. For this reason, we defined a time interval and lately a timer. The timer will call the method timer_callback, which must be implemented by us. Inside this method, we are going to calculate the joint values every 0.1 seconds, and the joint state message is going to be updated. Since time matters in ROS, we have to update the field timestamp in the header of the message. We want to keep actions separated from each other, so let's implement or define another method in our class, get_joints. In this method, we implement the real joint calculation. For instance, let the robot rotate along its z-axis of about 0.5 degrees every 0.1 seconds. Once a full rotation has been reached, we reset the body rotation joint to 0 again, and the robot can rotate again and again. Once the new joint rotation has been calculated, we update our joint state message. Remember always the definition order in your class attribute. In this case, since body rotation is the first element of the list, as you can see on line 27, we express the angular value in degrees. ROS, as all programming applications, wants radians, so we need first to convert from degree to radians by using the NumPy library. Now we can publish our joint state message by calling the publisher. Briefly, we update the body rotation joint every 0.1 seconds by adding to 0.5 degrees to the previous body rotation value and then send this updated value over the topic joint states. Compile the package and source the setup bash file. Remember to close this window because otherwise the position in those fields are going to overlap the values sent over the topic. Let's start our newly compiled package by typing ROS2 run udo and udo again. As you can see, the robot is rotating around the z-axis of about 0.5, decrease every 0.1 seconds. Only the first joint is updated. All the other joints are now update now. So let's stop now and let's add another movement pattern. For instance, let's say we want to move the arm up and down between a predefined range. Since we want to change direction of rotation in order to stay inside a predefined range, so we define another class attribute, self-direction, and initialize it to 1. If the direction is equal 1, the arm moves downwards. If the direction equals 0, then the arm moves upward. In any case, the arm should rotate of about 0.5 degrees in one of the both direction. Once plus 40 degrees has been reached, then the arm inverts its direction of rotation. For this reason, the self-direction attribute gets 0. moving downwards once the arm reaches 40 degrees. The attribute direction toggles to the value 1 and the arm moves upwards. Let's compile now our changed program and let's see how the now code affects the movement of our robot. As you can see, the arm is moving now downwards up to 40 degrees. Once that limit has been reached, the arm inverts its direction of rotation. Keep in mind that the rotation about any axis is determined by the right-hand rule. So looking carefully at the frame of the arm, a positive rotation around the y-axis leads the arm downwards. Finally, we can add a pattern to the manipulator. Let's add another if statement. If the position of the manipulator is smaller than 0.60 meters, then it must move forward of about 0.01 millimeter at any 0.1 seconds. Save, compile, source and start your node again. You can see that the manipulator is moving forward along the arm and then it stops when its upper bound boundary is being reached. To move the manipulator back, we should implement another branch in our last if statement. That's all for this lesson. Thank you very much for your attention. See you in the next lesson. Bye.